Hi, and welcome to our second episode of our Isometric game tutorial. Let's first look at where we left off last time. So, quick build and run. So this is what we have. Just a flat map in an isometric perspective. Today we're going to add elevation, because that's the main reason why we want to have a pseudo 3D environment. Meaning that we will have different height levels of this map and show them as such. So let's get started. So first let's think a bit about what that third dimension means. So I made some visuals to help illustrate this. So the idea is that if you increase a z coordinate, so a third part of our coordinate, that moves up where you want to draw the tile. We can call this a z offset, and in the case of this tile this is 0.8. We only move in the y direction of screen space, and you can find that those values again using an art program. So this is Pixelmator, but you can use any art program you want. So let's copy this layer and paste a new one. To find how much you need to display it, you just move it up until it makes sense. And we can see here that there's a delta of minus 8 pixels. For us it means we need to move 8 pixels because the y coordinates are inverted when in Pixelmator compared to SpriteKit. So that's where the 0.8 comes from. And if you have different types of if you use different tiles, then the value is probably different. So let's start there. Let's go to our code. And the first thing we need to do is we can write a test. Let's create a new location for third dimensions. And let's create a test that returns moving up one, increasing z by 1, increases screen space y by 8. So let's get an input coordinate. Can probably just reuse some of the code in this test. So let's create a new, let's say we go to this coordinate 0, 0, 1, and now we need a third component, and we expect to get back a 0 and 8. This one. Now this fails because our vector only takes 2 parameters, so let's fix that first. Let's go into our ISO converter and add a third component. This also means that we need to change up our other operations to take this one into account. And this one is now okay, but this, as you see, this doesn't compile because it now wants a z passed in. First, let's create the regular initializer that takes all the values, and then let's create a convenience initializer that just takes an x and a y, and then assumes that we have a z value of 0. That means all the other stuff will again compile. So we can do z self init, pass in an x, a y, and the 0. And the advantage is that if we go back to our tests and build, at least the other ones still work. Also, let's try and run our tests. And all the tests pass except the last one because we haven't implemented any third dimension stuff yet. So let's do that now. So let's go to our convert world to screen space function and let's add the z offset based on this definition. So this will be a vector of 0 and 8. And let's return a z world position z times a z offset. So let's run the test again. Now the test succeeds. So what we can do is we can add an additional case. So this one is slightly more complex. So let's try and get this one working as well. So I'll just copy this one. So we have 1, 0, 0, 1 returns 16, 16. So we take in this coordinate 1, 0, 1 and we should get back 16 by 16. So this one runs as well, and the linearity that we had last time also still works, so we can add just a couple of more cases. So let's rename this one to test our linearity for the third dimension, and let's get some input coordinates. We'll take this one. We'll also take this one, 1, 1, 2. We'll take this one that is on the negative, has a negative value in it, minus 1, 0, 1. And let's do the last one as well. That's minus 1, 2, and 2. And then we have our expected screen space coordinates. Those are also vectors. And the first one, 1, 0, 1, will be 16, 16. The second one is 1, 1, 2, will be 0, 32. Then we have minus 1, 0, 1, that's minus 16 and 0. And the last one is minus 48, 24. Okay, so let's go and loop through each and one of these. Let's see if this also succeeds. Okay, so our function works. Let's plug this into our game scene. So let's go into our game scene and let's assume we have a very simple height map. So we'll create a height map that's defined as an array of arrays where we have integers describing heights. So let's see, what do we want to do? Some of these. Let's first make one of these and let's add some elevation. So these will be slightly higher. This one is a bit higher. This is really high. and then again once. So we need to use this elevation now, so instead of just we need to change the way we look into the map a bit. So let's say for I in 0 until the height map count. So these are the number of rows we have. For X 0, the height map. For the ith row, let's go through all of these, and then let's see what elevation we have. And then we can do something like Z in. And then we need to copy paste a lot of this stuff, because that's more or less the same, although our the value here will be also have a Z. So we get the screen space position through the convert world to screen, passing in X, Y, and Z. We have a position, then we have a Z position, and we have the sprite. So let's try and run this and see what happens. And this looks kind of weird. And the reason is that the way we calculate depth here doesn't work very well. So let's have a look. Let's think about depth for a bit in the 2D space. Note that it worked for if we only have a flat surface. It worked before. But if you look at various coordinates, then we can say something about which thing is before which other thing. So I propose what we do is we create a function that calculates Z positions, and then we write a test to determine whether we get the correct and expected values back. So let's go into a test and let's look at depth. So we'll have a test. Let's create a function called, what do we want to call it? Convert world to Z position for 2D coordinates. And let's get some test cases in. So let's say we have some test cases, and these will be defined as an array of a coordinate. That's what we're looking at. And then we have an array of coordinates that it is before, and a set of coordinates that it is behind. So let's look at the first case. What we can do is we can quickly copy paste this and add this as comments. So this makes it a bit easier to write these test cases. So the first one will be a vector for -1, -1. This will have, it is before -1, 0, and 0, -1. So now we have an array where we pass in -1, 0, and 0, -1. Let's see, this is, what am I missing? Oh, and this one isn't behind anything else, so we can pass in an empty array. So this is our first test case. Let's copy this one. Our second test case is for 0, 0. Let's see, 0, 1 and -1. Let's see, 0, 1 and 1, 0. But this one is behind some other ones, so let's create a new vector here for -1, 0, and a vector for 0 and -1. And finally we have a case for 0, 1, that's before 1, 1 and 2, 1, but it's behind 0, 0 and 1 and -0. So let's go for each test case. And then for the before coordinate in test case before, we can assert that the function we're creating for the coordinates is greater than the one it obscures. So in this case our before coordinates, because larger values are closer to the camera and therefore obscure other ones. Now we don't have this function yet, so let's create it. So let's go into our ISO converter, create this function that takes a world space position, and this one returns it can return an integer. And let's see, how should this one work? Well, in our GameScene we had just to get it compiling, we first can just return a 0. So let's see this now at least compiles. We can also check the behind coordinates. And this is something similar, only it's checking not greater than, but the less than. And let's run this test. This fails because our hard coding is 0 as its return value. As a first iteration, let's just do what we did in the game scene and take the negative of the y position. So we take the world space position, take the z value and negate that one. Take the y value and negate that one. So this should work similar to what we are doing in the game scene. Let's run the tests, and the tests now pass. So that's cool. So let's do something similar. So let's write a couple of tests to check for 3D coordinates as well. We can do something very similar to the 2D version, but just rename it to 3D coordinates and copy paste these cases. Okay, let's see. So we have -1, 0, z1, and that one is before 0, 0, 0. Oh, sorry, and 0, 1, 0, and it's not behind anything else. Then we have 1, 1, 1. It is before 1, 1, 0, and it's also before 1, 2, 0, and it's behind 1, 1, 2, and 1, 0, 1, and the last one will be -1, 2, 1, -1, 2, 0. Let's see. And 0, 2, 0, and it's behind -1, 2, 2. Okay, so let's run these tests again and see what happens. And we notice that the tests fail. And that's because just looking at the y coordinate is not good enough anymore. Because let's go into our keynote value. What you'll notice that the y values can be the same for tiles with various z values. So for instance, this tile has a similar y value as this tile, and that although the z value is different, and that we need to make sure that this one has a larger z value, so it obscures, for instance, this one. So just taking the negative of the y value is not good enough anymore. So we need to do something extra. Well, one way to do this is to make sure that the first thing we could try and do is add a world space position.z, for instance, multiplied by the z offset. So let's see if this helps our tests. So now we see that the tests are a few more are working correctly and a few are not working correctly yet. And the reason is that because we also use the zPosition to offset the world space position y value, or I'm sorry, the screen position y value, these cancel each other out for various z values. So what we actually need to do is multiply this one again, so this one really gets added. So let's run the test again. And now we see the test succeed. So let's see if we can use this in our GameScene. So here we're calculating the z position. Let's just say we have a position for this vector because we need it 2 times. So now we can put the position here. And the z position we can use our convert world to z position for our position. And this is an integer, so we need to cast it. And I think if we now run this, we should see our map in the correct way. So this now works. So we are now able to use elevation and thus use a Heightmap to define what the game world should look like. So that's it for today. Next time I want to look at rotating the world. So thanks for watching. Have a good day.